microscopic expressions for mobility. You can see mobility is proportional to the average scattering time, right? And this scattering time in general decreases with increasing doping concentration. And this mobility is inversely proportional to effective mass. So if we have higher effective mass, then we will have a lower mobility. And we, here we just show you how does this, mobility changes. So this mobility decreases with increasing doping concentration, right? So this is true for all these semiconductors. So basically, higher doping can reduce scattering time tau. This is basically the average time between collision is reduced, right? So it can lead to a lower mobility. Okay, and also we discussed how the resistivity changes with doping concentration. So although the mobility decreases, right, but this end, the carrier concentration increases, and this end dominates. So the resistivity in general decreases with doping concentration. So this is because mobility decreases. The mobility decrease is less than the carrier density increase. Okay. And then we introduced the two important scattering mechanisms in semiconductors. At low temperature, this ionized impurity scattering dominates, and at high temperature, the phonon scattering is important. So overall, if we plot the mobility as a function of temperature, so the mobility first increases, then decreases. So it shows some peak at the low temperature. Okay, and then yes.
What happens if an electron encounters a hole?
I'm sorry.
You have a traveling electron and it encounters a hole. What happens?
Traveling electrons.
Yes, like in terms of scattering.
Yes.
If an electron runs into a hole, what happens?
This can also introduce scattering. Yes. So here so basically we only introduce these two types of scattering. Of course, there are some other scattering mechanisms can be important, especially in materials with higher electron concentration. So for example, this electron can also scatter with the electron. That's an important scattering mechanism in metals at low temperature. Okay. Yeah, but here we just focus on semiconductor materials, and these are, in general, these are two important mechanisms for semiconductor. Yeah, of course, there are some other, scattering mechanisms. So besides this electron scattering, we also have this the boundary scattering. So here, this is mainly focused on single crystals. So if we in the polycrystal, we have green boundaries. So the electron can also be scattered at the green boundary. There are several other scattering mechanisms. Here we mainly focus on single crystal semiconductor material. Right? So we also discussed the drift current. So this is a current resulting from the electric field. Okay, and so this is the expression for the drift current. So you can see this drift current is proportional to the electric field. Okay, and also based on these expressions, you can determine the direction for the drift current. Right? So basically, the direction is determined by the electric field. Right? So in today's lecture, we will introduce these new topics. So especially we will discuss the diffusion current, and you need to understand what is diffusion current. And this is quite different as compared with drift current, because they have different driving force. Okay, right? So here I just want to show you this band diagram, and also this band diagram can provide some information about this energy for electrons. Okay. So this y-axis is the total energy of the electron. Okay, so it's usually in like MeV or electron volt, and we have this EC and EV here, right? So at EC, if electron sit at EC, then this electron has zero velocity, has not zero velocity, and which means that this kinetic energy is zero. Okay, but if we have electron away from EC, like here, then its velocity is non-zero. So it has certain kinetic energy. And the kinetic energy is basically defined as the distance between this electron and the conduction band end. So basically it's this distance here is the kinetic energy. Right? And the potential energy of this electron is basically EC. So, okay, so EC here is the potential energy. Right? And so we can do the same, same for holes. Okay, and this, so basically, if the holes at EV, then the velocity will be zero, and then the hole has zero kinetic energy. If this hole is away from, like it's below EV, then it can gain certain kinetic energy, and the value of kinetic, the magnitude is basically determined by the distance between EV and here, this position here. Okay, and again, the potential energy of the hole is always EV. Okay, for this one, the potential energy for this hole is still EV. Okay, basically just draw some project lines, and we can find this EC or UV, the kinetic, the potential energy for electron and holes. Right? Okay, so basically the electron energy increases as it moves up. Okay, and similar hole energy increases as it moves down. Okay, so here you can see in the previous slide, so this is the electron energy, right? So this electron energy, it increases when it moving up. So here for the holes in the valence band, we can define a different y-axis. So this will be the whole energy. And the whole energy, you can see this is pointing down, which means that the whole energy increases with its moving down. Okay? Right? So, here we would like to try to understand this electric field and how does it affect this band diagram. Okay, so first of all, this EC, right? So this is the conduction band edge, and here we just assume it's a constant, right? But in real, materials, this can be a function of position. Right? So this is a potential energy of the electrons, and this can be defined as negative QV, and V is the electrostatic potential. Okay. So this is basically this is the definition for the potential energy. So it's related to electrostatic potential, and also we know that what's the electric field? So electric field, as we discussed in the last lecture, right? So electric field is due to the gradient in electrostatic potential. Okay, so it's related to this equation here. So if we just assume along the x-axis, so this electric field will be negative dV. Right? we know this V is, EC is negative QVX, right? So we can change this to, this DEC over DX. Basically, we just multiply by this negative 1 over Q, right? Multiply by negative 1 over Q here, so these two negative sign cancel out, so there's 1 over Q here. So here, this expression is very important. So you can see this electric field, right? So electric field, so it's related to this DEC over DX. So this is the slope, right? So this is slope. The DEC over DX, this is slope of this EC. And of course, if you can see here, if this here, this figure here, EC is constant, which means the slope is 0. And in this case, we have electric field is 0. But in some cases, if we apply this non-electric field, right? So if this electric field is non-zero, then we will basically tilt EC. So EC will not be a flat line. Okay. So this is the case this is basically the Venn diagram. If we apply a electric field, okay. So here you can see we have a voltage source here, and we connect to the right side, right? And this is just grounded left side. So this can introduce electric field, and this electric field, can change this, the slope. So basically, the EC, EI, or EV will be tilted, or EM. All these are will be tilted. And you can see, right? So if this is positive, right? So this voltage source is positive, then the electric field will pointing to the left, right? So this electric field pointing to left, and this is consistent with the definition here. So if it's pointing to the left, and we define the axis is pointing to the right. So it means that this electric field is a negative value, right? This negative value because it's pointing to the opposite direction of x-axis. And then you can also look at this expression here. And you can see this DEC, the slope of EC is a negative value, right? The slope of EC is negative value. So basically, we have to define, right? This is axis and this is y, right? If we have some line like this, then the slope is positive, right? This is slope positive. But if we have something like this, then the slope is negative for this line. Right? And you can see this is negative, so it's consistent with the electric field direction. Okay, so here you can see that the electric field direction can be determined by the slope, or how this EC or EVEI are tilted. So if tilted this way, the electric field is pointing to the left. And if tilted in the opposite way, right, like this, the electric field will pointing to the right. Okay? And you can see because in general, EC, EI, EV, they are always, because they are always parallel with each other. Okay? So their slope will be the same. So you can either look at EC or EI or EV. They are same. They have same slope because the band gap here is always a constant for the same material. Okay? Right? And also, this is also related to this equation. Right? So this is the definition of EC, right? So this EC is related to minus QB, and of course we can define certain reference level here, and we can see if we increase the voltage, right? So if we increase the voltage, and because with this we have minus sign here, so EC will decrease, right? So this can also be understood like this way. So we basically positive voltage pulls down the band. This positive voltage pulls down the band. Okay, so this is electric field, and how does the electric field affect the band diagram? And also based on that we can also determine the energy for either electrons or holes. Okay, and for example, in electric field, so basically, if we have electron here, it can move to the position B, right? So you can see the total energy is the same. So remember this x-axis, sorry, y-axis here, this is E is the total energy electron. So let's give some numbers. So this is 1 and this is 2, right? So the total energy is the same if we move from A to B. And now, so basically, now what are the potential energy and the kinetic energy for these two electrons? For the electron at this position A, what is the potential energy? So let me go back to the, so basically potential energy is EC. Okay, so just find the corresponding EC value. Okay? So what's the potential energy for electron position A? What's the potential energy? 2. Yes. So basically it's EC, right? So basically you just draw a corresponding line here, and this will be 2. Okay? So just around 2. Right? So basically, and how about kinetic energy for A?
1.
Kinetic energy. Remember, what's the definition for the kinetic energy?
So you don't have mv squared.
No, kinetic energy is defined here. So it's distance between this position and EC. Okay? So if the electron is at EC, then the kinetic energy is 0. Okay? So now how about this one? What's the kinetic energy?
Assuming it's at point B.
A. Point A.
0.
0. Yes, because it's at EC. Okay? How about B? What's the kinetic energy?
1.
1. Yes, good. So 1 is basically the distance from here to here. That's 1. And what's the potential energy for B? 1. Yes. So basically, just find the corresponding EC value. Just draw a line here and find EC value. So this is 1. Okay. Right. And you can see that the total, yes.
What's happening to the band gap when EC was applied?
The band gap is unchanged.
It's unchanged?
Yes, so that's why EC is parallel to EB. Yeah. Okay, right. So now you can see for A, the potential energy is 2, kinetic energy is 0, right? And for B, the potential energy is 1 and kinetic energy is 1. And you can see that overall the total energy, right? Total energy are same, right? Total energy are same. So basically you can see in the electric field, the electron trades off potential energy for kinetic energy. Because the electron will move along this direction, move to the right. If we have electric field pointing to the left. Okay, so electron will always move against the electric field, right? Right. So you can see that in the absence of scattering, the total energy is conserved. The total energy is basically potential energy plus kinetic energy. You can see for A and B, they have the same total energy. And with scattering, the electron rolls down. If there's not scattering, then this total energy can be reduced, so it gets basically electron rolls down, like on this way. And we have same story for holes, right? And because basically holes, will move along the electric field direction. So basically, the holes will move to the left. Okay, and with scattering, holes will float up here. Okay, holes are moving. Holes basically with scattering will move around this direction, and this electron will move this direction with scattering. And here, what's the direction? Is the electric field going in? Going to the left. Right, how to determine this? How you can tell it's from the left, pointing to the left?
Because it's going to the right side.
Yeah,
So
yeah. But if I don't have electron here, only show this band diagram. How can determine the electric field direction?
Holes are clustered so they follow the
Yeah, you can do that. You can assume there's electron falls down, right? And the electron moving direction is opposite to the electric field direction. You can do that, but you can also use what we have learned here, right? So what we learned here, this is the definition of the electric field, right? It's related to slope, right? And if this slope is negative, right? It's negative, which means that it will be it will be along the minus x direction. Right? Okay. Any questions? Okay. Right, so here I just want to show you some simple like this water analogy to understand the electron and hole moving directions. So basically electrons sink and holes flow. So that's only 4 words. You can understand this, right? Try to memorize these 4 words, and you can determine the electron and hole moving directions. And we can use this water analogy. So basically, the electrons in the conduction band will be similar as this, some water, right? Water inside like almost empty bottle, right? If we tilt this empty bottle, then this water will flow towards the bottom, right? So this is basically electron moving direction. Okay, so this is electrons sink. And for the holes, like think about almost 4 bottle. Okay, the 4 of water. And if we tilt this bottle, we have this bubble. The bubbles can flow up, right? So this is symbol. These bubbles are, similar to the holes in the valence band. So basically, holes flow. Okay, so use this water analogy. You can determine this electron and hole moving directions. here I have two more questions here. So what direction is the electric field pointing? So hope we can understand this. To the left or right?
Right.
Right. Okay. Yes, to the right. So you can solve this using two ways, right? First is based on this water analogy, right? So because holes are moving to the left, right? Oh, sorry, moving to the right. Holes are moving to the right because holes float, and this whole moving direction is the same as the electric field direction. Okay, so this is one way, and another way is using the definition of the electric field. Right? The definition is related to the slope, this dEc over dx, and here this slope is positive, right? So this positive, which means this along the positive x direction. Okay. Right? And also, how is the voltage applied? Okay, and which side is positive? And for this one, you need to understand that this positive voltage pulls down the band. And this is what we have showed you before. So if we have this positive voltage applied here, then EC will be reduced, right? So in this case, the positive voltage will be applied on the left side. Okay, so we'll have this will be positive voltage on the left side, so we can pulse down the band. Okay, right, and use water analogy, we can also understand, why there's no current for a completely filled band or empty band. Okay. So if we have valence band with no holes, so this will be identical to the equivalent to this completely full bottle, right? And if we tilt it, there's no flow. There will be no flow. So it's basically a completely full band carries no current. Okay, so if we have complete full band, there will be, if we tilt it, still no current. Right. So this is a tube for semiconductor at 0 Kelvin. Right. At 0 Kelvin, we have completely empty conduction band and completed full valence band. And even we apply electric field, then there is still no current at 0 Kelvin. Right? Okay. Right. So, any questions about this water analogies? Okay, so hope you can understand this. We will have, we'll definitely have some, some, question related to this in the midterm exam. Okay, so make sure you understand this. And also this band diagram is very useful, right? Where you can understand this, many informations. Okay, right. Right, so now let's move on to this Fermi level in equilibrium. Okay, so in equilibrium, this Fermi level is constant and independent position. Remember the Fermi level, the definition of Fermi level is, when we think about the Fermi function, right? So for the Fermi function, if the energy of electron is same as the Fermi level, what's the value for the Fermi function? 1/2, right? So this is the definition, right, for the Fermi function. And you will see that in equilibrium, this Fermi function EF is a constant. and it's independent of position. So which means that the Fermi function, if we draw the Fermi function, it will be like horizontal line, right? So now let's try to prove this. Okay, just want to just show you the conclusion first, then let's try to prove this. So to prove this statement, we need to use this so-called detailed balance. Okay, so it means that in equilibrium, all these microscopic processes are balanced, and this is very similar to this this Chinese philosophy. It's like yin and yang, right? They're all balanced with each other, and in semiconductors, we can also think about there are like two different materials. They have different density states, and also they have different occupation or this Fermi function, right? And if we put these two materials together, then these electrons will start to transfer, right? Its electron will transfer, back and forth, and if it is in balance, right? If it's in balance, then what can happen? So if everything is balanced here, so we have this transfer rate. This is transfer rate from material 2 to 1, and this transfer rate from 1 to 2. So if everything is balanced, right, then this transfer rate will be same. Okay, so this R12 should be same as R21. Okay, so this is the equilibrium position. Everything is balanced. Now, with that, let's try to prove that this Fermi level in these two material is the same. So to do that, let's try to find the expression for this transfer rate. Right? So we have transfer rate from 1 to 2, and basically we are thinking about this electron, right? Electron moving from material 1 to material 2. Right? So we need to think about how many electrons do we have, right, in material 1, and in material 2 there must be some empty states, right, which can hold these electrons. Okay. So this transfer rate is related to the number of this field state in material 1 and number of empty states in material 2. Okay, so number of field states is basically related to the density states, right? The density state here we use this N1, and the occupation is basically F1. Okay, and in material 2, the number of empty state is still the density state. Then we need to consider it's empty. Then this would be 1 minus F, right? So this is basically number of kind of think about this number of holes, right? Right. So this electron can move to this hole, and they can find this certain position, right? And similarly for this transfer rate from material 2 to material 1, so it will be proportional to the number of field states in material 2, which is N2 times F2. And also it's proportional to the number of empty states in material 1, which is N1 times 1 minus F1. Okay? And this here, this F1 and F2 here is related to this kind of Fermi function, right? Fermi function, and the difference is, let's assume in the beginning we have this this EF1 and EF2. Okay, define this Fermi level in these two materials. So in equilibrium, since there will be no net flow, of carriers or energy, right? If there's some net flow, then this carrier concentration will keep increasing, right? But in equilibrium, remember I told you that everything is balanced, and the property is, is kind of constant, right? So it cannot change. So this in equilibrium, this transfer rates, these two will be the same. So we can set about the expressions equal. So the density of state term cancels out, right? So here basically you can see the density of state term, because if we, these are, we have both, M2 and M1 in these two expressions. Right? So these density of state term cancel, and what we left is, F1 minus F1 times F2 equals F2 minus F1 times F2. And again, you can see this F1 times F2 cancels out. They are same. So what left is just, we have F1 equals F2. So, which is this expression, right? To satisfy this, equation, we must have this, the Fermi level, will be same, right? The Fermi level must be same in these two materials, okay? To satisfy this, right? Right. So that's two, materials, and again, we can make, make these different material sections smaller and smaller, right? And then this equation will become something like this. So this dFe over dx is basically this gradient in Fermi level equals 0 in equilibrium. Okay? So this is very important conclusion, and we will use it a lot when we study the band diagram. Okay? So it means that, if the Fermi level is constant, independent of position, then the system is in equilibrium. Okay? We can derive from this to this, and again, if the system is in equilibrium, so opposite way, if the system is in equilibrium, then the Fermi level is constant, independent of position. Right? And also, if we plot the Fermi level for a system in equilibrium, so we just plot the Fermi level as a horizontal line. Right? So the Fermi level will be horizontal line. It doesn't change with x. Okay? So this is Fermi level in equilibrium. Any questions about this? Okay, right, good. So now let's move on to this diffusion current. Okay, so we introduced the drift current, and the drift current is due to the gradient in this electrostatic potential, or it's due to the electric field, right? So if we have an electric field applied in the material, then we will have this drift current. And this is a expression for drift current we derived in the last lecture. Now, today we're trying to understand, how about these two? Okay, if we have gradient in electron concentration, or if we have gradient in hole concentration, so what can happen? So this can, these gradients can actually give rise to so-called diffusion current. Okay, and these are the two expressions for the diffusion current. These are for electrons, and this is for holes. And we will try to prove this equation. Okay. Right. And here, just for simple, for simplicity, we just assume here, just assume a 1D case, or then we just assume along x direction. Okay, right? So for diffusion current, we basically we're thinking about if there's a concentration gradient, right? If there's concentration gradient, and here we are showing this the electron concentration is not uniform. Okay, so it's higher on the left side and it's lower on the right side. Okay, so if there's a gradient in this carrier concentration, then we will have the diffusion behavior. Okay, and this is similar like if you drop basically some ink in the water, right? And this ink molecules will kind of diffuse to this water, right? So here, if we have electrons, higher concentration on the left side and lower on the right side, then electron will moving from high concentration region to the low concentration region. Okay, so which means the electron will move to the right. Okay, so this is electron moving direction. So then we can try to determine this particle flux. Okay, so this particle flux is related to the diffusion coefficient. Okay, so this diffusion coefficient is defined as this is this particle flux. Basically, it's weighted particle flux, and this carrier concentration gradient. So if we know this carrier concentration gradient and also the diffusion coefficient, then the particle flux can calculate. Okay, so remember there's a minus sign here. Why there's a minus sign here? So think about this, right? So this is a gradient, right, in carrier concentration, and if we have this kind of distribution, then this this gradient will be a negative value, right? Because the slope is negative value, and that's why we want to have another in this negative sign here. So make sure this particle flux is along the x direction. Right, positive x direction. That's why this is on positive x direction. Okay, and this is true for holes, right? This is the hole density like this. So the holes will diffuse from high concentration region to the low concentration region, and this is the hole flux. Okay, and the unit of this particle flux is 1 centimeter squared per second. So basically, number of particles passing through certain unit area per unit time. Okay, and again you can see it's the particle flux always moves away from the gradient. Okay, that's we have the minus sign here. And to calculate the current, we need to multiply by charge to get the electrical current, right? And we know for electrons it's negative charge, so it's minus Q, right? And these two, the minus sign cancels out, right? So we have QD, this gradient in N, and we can do same, same for holes. So the holes are positive charge, so that's why we have plus Q, and then we will have the final expression, we will have this negative QD gradient in P. Okay? Right, so these two are the diffusion current. Okay, for electrons and holes. And you can see for electrons, right? For electrons, the diffusion current is you know, in this case, right, the diffusion current is pointing to the left, pointing to the left. Okay, and this is because, you know, basically because electron is negative charge. Right? If electron moving to the right, then the corresponding current will moving to the left. Okay, but for holes, right? Holes, because holes are positive charge, right? If holes are moving to the right, then the corresponding drift current, diffusion current, will have the same direction. Okay, so this, you know, there's difference here. The direction are different. If we have similar moving direction for electron holes, and this is because they have, you know, opposite charge. Okay, right. So this is the, you know, two equations. So this is the diffusion current. So carriers diffuse away from regions of high concentration to the regions of lower concentration, and this can lead to diffusion current. And these are the two expressions for we derive. And, you know, again, if we only consider 1D case, right? So this gradient in n can be replaced by dn over dx. Right? So that's the diffusion current. Now, if we consider the total current, right? So if we have both electric field and the gradient in carrier density, then we will have both, you know, we will just need to add this, you know, drift current and diffusion current together. Right? So the total, you know, the total electric current will be like this. Okay? And this is total hole current. Okay? And you can see there's, you know, some difference here. So just highlight here. So this, we have this minus sign here for the whole current. Okay, so now if we want to, you know, if we consider both electron and holes, and then we need to add these two current together. So this is total current. So total current, we need to add this Jn plus Jp. Okay, so now you can, you know, easily calculate the current if we know the electric field and also the gradient, right? Gradient in carrier density. Okay. Right. So just want to highlight this. Any questions about this, you know, total current? Okay. So here I just want to highlight here, so you can see that this term, right? So this term is due to the electric field, and this term is due to the gradient in carrier density. And you can see for electron diffusion current and hole, for electron drift current and hole drift current, you know, they have the same direction. So you can look at this expression. The direction is determined by the electric field. If you know the electric field direction, and these two are along the same direction. Okay? And but this, you know, for the diffusion current, because we have this, you know, this plus sign and minus sign, so this can lead to some difference in the you know, diffusion current directions for electron and holes. Right? Okay, so next I would like to show you an important relationship. And remember, we in this current expression, right? So what's mu? Mobility, right? And what's d? diffusion coefficient here. Okay, so it's the diffusion coefficient to be some constant for certain material. So this diffusion coefficient, and the mobility is in this. This is a drift current, and the diffusion coefficient is in this diffusion current. So now actually there's certain relationship between these two, mobility and diffusion current coefficient. Okay, and so this is called Einstein relation. So this relation between diffusion coefficient d and mobility mu. So this is very useful equation. So this d over mu equals kt over q. Okay, so d over mu equals kt over q. And what's k? Boltzmann constant, and T is temperature. And what's Q? Charge, right? Electron charge. Okay, so all these can be constant, right? For a fixed temperature, right? So then, if you know D, you can calculate mu easily. And otherwise, if you know mu, you can determine D easily. And this relationship is, is both valid for electron and holes. Okay, so we can have this d sub mu equals d sub n over mu sub n equals kt over q, or d sub p over mu sub p equals kt over q. Okay, so now I would like to show you how to prove this. Okay, so to prove this equation, we need to use the carrier density expression we have learned before. So we want to start with this equation. Okay, so remember this is the whole concentration is related to the intrinsic carrier concentration, and it's related to this EI minus EI. Okay, so start with this equation, and we can take the derivative on both sides with respect to x. Okay, so here we just treat this p as a function of x, and also we treat this EI and EF, they are also a function of x. Okay, so then we just take the derivative. So we have this dp over dx on the left side. On the right side, if we take the derivative, so basically the exponential term, right? We have this exponential. So this exponential term here, let's just write down here. So it will be, so it was d n I exponential EI minus EF over KT over dx. So Ni will be a constant, right? For this exponential term, this derivative will be exponential term itself, right down here, minus EF over KVT or KT. And then we need to do the derivative with this term here, right? So we multiply by 1 over KT, and we will have this DEI over dx minus DEF over dx. Okay, so now what's this? What's this? This N or P? This will be P. Yeah, this is a P. Okay, so that's why you can get this, this expression here. Right? So because P1 over KT and d di over dx, df over dx. And we know this is in equilibrium. So in equilibrium, this Fermi function does not change with position. Okay? And now we can get an expression for this dEI over dx. Oh no. So this is di over dx is related to this related to this v, the electrostatic potential, right? We have discussed before. So this is what we have showed you. Here. Okay. Here. So it's related to the gradient in this voltage. Okay, so it's di over dx related to the dV over dx, and we know this minus dV over dx is electric field. Okay, so that's why we have positive QE here. So now we can just replace this dEI over dx by QE. Okay, if we replace this dI by QE here, then we will have this dP over dx is will be this PE Q over KT. Okay, and in equilibrium, because everything is balanced, right? In equilibrium, this total current, this total whole current will be zero, or total electrical current will be zero, or total current will be zero. So this this expression here will be zero. Okay. So now if we replace this dP over dx by what we have derived here, replace this dP over dx, we'll see that a lot of terms can be cancelled out, right? Because we on these two terms we both have P, both have Q, and also have E, right? And we can reorganize this. We can get this mu minus dQ over KT is zero, and that's why we can get this dP over mu P equals KT over Q. Okay, so this is how you derive the Einstein relation. And of course, you don't need to I will not ask you to derive this equation during the quiz or the final exam. Just need to know the meaning for this relationship, right? And you should know how to use this Einstein relationship. Okay? Right? Okay, so that's just Einstein relationship. Any questions? Okay, so basically it's very useful. If you know D, you can calculate mu. Or if you know mu, you can calculate D. Okay, so usually we set this T as pretty much room temperature. Okay, and it's both Q and K are constant. Okay, so to summarize, we have introduced this very useful expression. So if this D, the Fermi level is constant, then the system is in equilibrium. Right? If the system is in equilibrium, the Fermi level will be constant. And also we discussed how does this electric field change the band diagram. So basically it can tilt the band diagram. And this tilting direction is related to the position of this applied voltage. Applied voltage, basically positive voltage pulls down the band. Also you need to understand how to calculate the kinetic energy and potential energy for this electron and holes. So again, I want to emphasize, for this one, the EC is always the potential energy. So this one, EC will be this value here, And for the electron at this position, you need to draw a line here to the corresponding, to find the corresponding EC. Okay, draw a vertical line and a horizontal line, you can find the EC value or the potential value for this electron. And kinetic energy is always the difference. So the kinetic energy is like here for this electron, and the kinetic energy is 0 for this electron because it's sit on the EC. And also we introduce water analogy, and this can be used to understand electron and hole moving directions. And this is also, we introduce the diffusion current, okay, and Einstein relation. And we still have some time left, so that's why I want to show you some examples. So we talked about there are two types of current, and from two different driving forces. What are these? What are these two types of currents? Drift and diffusion current. Yes. So what are the driving forces? For the drift current, what's the driving force? Say again. Electric field. It should be electric field. Okay. For the diffusion current, what's the driving force? Mobility? No. Okay, so go back to the equations. Okay? So go back to the equations. So for example, this is the expression, right? So which one is the current, the diffusion current?
Alright.
The right one, right? So this diffusion current and this drift current. Right? So you can see for the drift current, the driving force is E. Okay, so electric field. You can see this, the magnitude and direction are determined by E. Okay, and for the diffusion current, what is the driving force?
Gradient.
The gradient, right? So because this Q and D are constant, right? So it's the J is determined by dN over dx. So this is a gradient in carrier density. Okay, so these are the two driving forces: electric field and the gradient in carrier density. Okay. Right? And this is a very important example, and I hope you can answer these questions. So if we have this kind of band diagram for a material, let's try to answer these questions and also provide some explanation. So is it N-type or P-type? It's an N-type, true or false? So if we have this kind of band diagram, BC, EB, EI, EF, and EAZ. So it's N-type or P-type? Yes,
P-type
P-type, why?
is the Fermi levels underneath the intrinsics.
Yes, exactly. So this will be a P-type because the EI is below EF. Okay? Right, good. Now, third one, it is in equilibrium, true or false? True or false? True, why? From that way is not changed. Yeah, exactly. So if you want to check whether the system is in equilibrium or not, you just need to look at the Fermi level. Okay, let's focus on Fermi level. If the Fermi level is constant, then it's in equilibrium. If not, then it's in basically non-equilibrium. Right? So basically the Fermi level constant, and it's in equilibrium. And there is a whole drift current. True or false? True. Why?
This is a non-zero electric field.
Yes, yes. Okay, so what's the electric field direction? Left, yes, left, because the slope is a negative value, right? Slope is negative, or you can use the water analogy, right? The electrons thing, right? So electron are moving to the right, and electron moving direction will be the opposite to the electric field direction. The electric field will be pointing to the left. Okay, so there will be a whole diffusion current because this E is non-zero, and we have showed you this the direction of electric field is pointing to the left. Then what's the direction for the current? The whole current, whole drift current. Left, right? It's left because you can see this J, the direction of J is determined by E, right? And if E is pointing to the left, then the J will be along the same direction. Okay. So next, there is a whole diffusion current. True or false? Simon, what's the driving force? Diffusion current. Driving force for the electric field is the driving force for the drift current, right? So what's the driving force for the diffusion current? The gradient, right? The gradient in carrier density. So now let's see whether the carrier density is uniform across the material, or there's a gradient. Whether the whole concentration is uniform inside the material. It's uniform or not, the whole concentration? Does it change with position x? So think about some equation we derived before, right? So this is the equation for whole concentration, right? And we can see this position or the magnitude related to this EI minus EF, right? So it's whether this EI minus EF is constant in this material. It's not, right? So basically this EI minus EF is higher on the left side, and EI minus EF is smaller on the right side. Okay? So which means that the whole concentration is higher on the left side. Okay? So the whole concentration is not uniform. So there's a gradient. So there must be a whole diffusion current. Okay? Right, so just look at this Venn diagram. You can see this position between EI and EF can tell you, how does this whole concentration change. Okay, any questions about this problem E? Okay, right, so next, is there a electron drift current? True or false? True, right. And what's the direction? Right? drift current, right? For drift current, look at this expression. So this is drift current for electron, right? And you can see this drift current direction, J, is same as electric field. And we have shown the electric field is going to the left. Okay? So you can see the drift current for electron and hole are always same. Okay? And last one, is there a electron diffusion current? True or false? True. Okay? So there must be some, concentration gradient, right? So this can also be used, you can also use this equation here. So this is the expression for carrier electron density. And if we look at here, again, this EI is changing, right? And you can see, if we just do a simple calculation or simple comparison, you will see the electron concentration is higher on the right side. Okay? And then if electron is higher on the right side, electron are moving to the left. Right? Electron or holes, all of them are always moving from high concentration region to the low concentration region. So electron are moving to the left, and then the corresponding electron diffusion current will along the opposite direction because electrons are negative charge. Okay, so this electron diffusion current will pointing to the right. Okay. Right. Any questions about this? Right. So last one. So what's the direction of total electron current? It's a little bit difficult one. Left or right? Okay, neither. So this is because the system is in equilibrium. Okay, so when this, because we have Fermi level is constant, so the total current will be zero. Okay, for both electron and hole. Okay, so total electron current is zero, total hole current is zero. And you can also tell from here, it's kind of your balance. So this is electron drift and diffusion current, we have along opposite direction, and then the hole and the electron are also in opposite direction, so we cancel each other. Okay.